All right, so where were we? We were yesterday. We were looking at this maximum likelihood estimation. We talked about the main objective is, for example, classification. For example, we want to estimate this class conditional density, and we saw the challenges it posed. One of it being the curse of dimensionality. And and we are going to approximate it by we are going to assume some parametric form for this conditional density, and we are going to estimate those parameters given the training data which we have. So this is our training data. So so D is the training data. So we have to do this for all the classes, and we compute what is called the likelihood function, because we are now going to see the likelihood as a function of the parameters. There is a parameter vector which is unknown, and we need to estimate the parameter vector, and that is done by evaluating this likelihood function for various values of the parameter vector. So for example, if this is the likelihood function, and find out those estimates where the likelihood is maximum for the data which is given. So typically the likelihood function is seen as a function of parameters. It's not a function of the data, it is a function of the parameters. Because once we have the training data is fixed, that we are not going to change. So we saw some things which will be useful to us, gradient operator, Jacobian matrix, and some useful results which we will use. And this is essentially the gradient operator. And because these samples are IID, the samples in the data set x1, x2 up to xn are IID. We can evaluate the likelihood. We can evaluate the log likelihood, and by taking the log, it becomes a sum. Because it is independent, it becomes a product. I have written here this P likelihood of theta. This P of D given theta is going to be, because this is your D and these are IID, so this becomes a product, and when you take the log, you can you get the sum, and then you're going to apply this gradient operator to this sum. So the gradient operator is with respect to theta, because we are going to find out the local maximum, and so this we evaluate it to 0. And this is a necessary condition because there could be other maxima also. So we really don't know if that is a local maximum. Okay, and we mentioned about the map estimate, in which we give some weightage to the likelihood. We give some weightage to the likelihood, and we will give more weightage to the more likely likelihood values. We'll give more weightage to the more likely parameter values. We're going to have a prior for the parameter. And for example, again, looking at the child and the height and weight example for child and adult. For, let's say, you're doing it for a child. So a reasonable value for the parameter is, let's say, height maybe like 3 feet and weight maybe like some 30 kilos. So you should give more weightage to those values rather than values like height being 100 and weight being 200. There's no point in giving weights there's no point in evaluating the likelihood for with the same confidence as what you do for 30 and 3 feet, yeah, because that is more likely to happen. So that is done with the help of this prior. So this becomes what is known as the map estimate. We'll see that later. Right. So what this means. So let's get back to what we will do today. So all of this material is from Duda's book. So now to start with this, let us just do it for ML. Let's do the ML estimation. We are going to do it for the Gaussian case. I'm following it directly from Duda Hut. You can refer to it. And just for illustration, what we will start with the simple case. We're going to assume we have an unknown mu and a known sigma. So this is a multivariate Gaussian. So our parameter vector theta will have, let's say it is in a d-dimensional space. So we will have mu1, mu2 up to mu d. Then you will have the n into, what shall I say, n into n minus 1. So if in the covariance matrix, right? Yeah, so in the covariance matrix, the diagonal entries and the lower triangular portion is what we want. And this we saw has n into n, okay, not n. So d into d minus 1 by 2. Values are there here. So those values will come here, those parameters. I will just call this as, just to make my life easier, I will just call this as set A. Okay, I'm just calling this A. And so that A comes here. Okay. So this A consists of essentially the diagonal entries and the lower triangular entries, because this is a symmetric matrix. So we are, in this case, we are saying this is known. So these are the parameters which we want to estimate. And this is nothing but your mu. This is what we want to estimate, right? So like yesterday, we are given a data set D, which consists of vectors x1, x2 up to xn. No, we know beforehand that this is coming from this particular class, the current class of interest. So now let us, now we are going to assume, we are assuming that the P of x given C is a multivariate Gaussian. It comes from normal, unknown mu, and known sigma. Okay. So it is the maximum likelihood estimate of the mu which we want to find out. So we can write this likelihood function. One second. I'm just trying to find a more comfortable position to write, which I don't have. Let's see. Where are we? Yeah, so we have the D. So, sorry, no place to write. Okay, fine. So let's now find out the likelihood for one point. Likelihood log of P of xk given mu. This mu is currently unknown. Okay, we are assuming this mu is currently unknown, but we are so just to explicitly say that we are conditioning it on this unknown parameter. So if I write it out, it will become half of log 2 pi d determinant of sigma minus half xk. So this is just xk minus mu transpose sigma inverse xk minus mu. Right, I'm just writing out the likelihood with respect to Gaussian. And now we need to, what do we have to do next? This is for one particular point. So what do we have to do next? What should we do next? Somebody has to say something. What should we do next? What should we do next? We've done this bit. Here the summation is not there. We have just done it for a single point now. Okay. Okay, this online class is not leading anywhere. Ananya, you're here, right? Ananya, you're in Dawn Lab. I mean, you're in Manas Lab. Ananya? Okay, she's not there. B2173. Yes, are you there? B2173. Yes, are you there?
Sir, my mic was not working. Yes.
Yeah, sure. Okay. Can you tell me what we should do next? I've written this likelihood. Now, what should we do next? Any idea?
So we need to estimate the maximum likelihood.
Yeah, that is what we are doing. But how do you do it? This is the likelihood. This is the likelihood. How do you find out the maximum now?
So differentiate with respect to xk.
Differentiate with respect to xk. We are seeing that this likelihood is a function of what now? What is this likelihood a function of? This likelihood is a function of what?
That the feature points x1 to xk.
No. Likelihood is a function of the parameters. So the parameter here is mu. So we need to evaluate. We need to differentiate this. That is correct. But with respect to mu. Okay, with respect to the mean vector. That is what we need to differentiate. K given mu. So I'm saying given mu, but actually currently the mu is unknown. Okay, for some unknown mu, we are going to differentiate this. And so let's differentiate. How do we differentiate? So anyway, this term does not have a mu. So this goes off. Now we need to differentiate this. So let's differentiate this. Let's expand this to make it easier. So I have we are going to do the differential of minus half into xk transpose sigma inverse xk minus xk transpose sigma inverse mu minus mu transpose sigma inverse xk plus mu transpose sigma inverse mu. Okay, this operator we are going to apply on the whole of this. So when you do that, what do you get? Yeah, what do we get? There is no mu here, so this goes off. This is equal to 0. And this also, we said, this is also going to be equal to 0. There is a mu here, xk transpose sigma inverse mu. So make use of, and we are going to differentiate it over mu. So make use of the result which we used yesterday. This is of the form x transpose a y, right? So x transpose a y in here, y transpose a x is written here. So, and we are differentiating it with respect to mu. Okay, so in this case, if you compare it to this, it will be with respect to the first one, which will give me this will give me xk transpose sigma inverse, and here it is similar form, but it is the mu is coming here first, so that has a slightly different form, which is minus mu transpose sigma inverse transpose, but actually the I mean, one of them is the transpose, but sigma is symmetric matrix. So sigma inverse is also symmetric. So sigma inverse transpose is same as sigma inverse. And what else? We have this term also. We have to, that is again with respect, so there is a quadratic form here. What did we do here? With respect to x transpose AX. Okay, x transpose AX. That also you will write it in the form plus.
Sir,
Yes.
so the second term will be sigma inverse xk transpose.
Which term? This one.
No, sir, the other one.
This one.
Yes.
Sigma inverse
Xk transpose.
Okay, we'll come back to that. Wait, let me just finish this. What is this? This will be mu transpose sigma inverse plus sigma inverse. Okay, sorry, what were you saying? You're telling about this. This is of the form y transpose a x, let's say, and we are going to find d. We are going to find this with respect to, so dou of y transpose ax by dou y, right? Because our mu is what we are going to differentiate over.
Yes, sir.
What do we have here? Y transpose ax. Let me see what I wrote. Y transpose ax dou alpha by dou y is X transpose A transpose. So X transpose A transpose. What is my X transpose here? Oh, sorry. So this you are saying is
X
X transpose sigma inverse.
Yes, sir.
Okay, transpose sigma inverse. The other terms are correct? Other terms are correct, no? Mu transpose plus sigma, I know sigma inverse. Okay, so let us simplify that. How can we simplify this? I need to write it down. Wait. What are we getting? Are we, there is a minus half outside. There is a mu transpose sigma inverse. So there is a half there. This will be 2 sigma inverse. So this will give me, so this is X transpose sigma inverse, right? Again, there is, it will become 2 and there is a half there. So finally you should get X transpose sigma inverse minus mu transpose sigma inverse, which I can write it as X transpose minus mu transpose sigma inverse, which is also the same as sigma inverse xk minus mu. Okay, because AB transpose, I mean, A transpose B transpose is BA the whole transpose. By using all that, I will get this. And this is the one which we are going to put it equal to 0. Okay, this is actually for just for one point, one particular xk. So now if you for all xk in D, we have what are we going to do? We are going to now sigma k equals to okay, 1 to n sigma inverse xk minus mu equal to 0. This is, so if it is actually the mu is equal to mu hat is the optimum mu. Okay. So if mu is mu hat, then this is equal to 0. Okay, so now let's expand this. So this is sigma inverse. I'll take it out. This is nothing but xk are vectors, xk minus mu hat, x1, I'm going to remove the summation, x1 minus mu hat plus x2 minus mu hat, so on, xn minus mu hat is equal to 0. So now this is already known. The sigma inverse is already known to us. and that cannot be 0. So that means summation of xk, k goes from 1 to n, minus n mu hat is equal to 0. So this gives us mu hat is equal to 1 by n sigma xk. K goes from 1 to n. Okay, so what did we just write here? What did we get here? The maximum likelihood estimate for, in this particular case, with the known sigma, with the known sigma and unknown mu, is nothing but 1 by n sigma, the sum of all xk's. And what is this term actually? What is this actually? You have the data set D. It has x1, x2 up to xn. And we want the maximum likelihood estimate. I'll call it mu ml. And we just saw that mu ml is nothing but the x1 plus x2 xn divided by 1 by n. These are all vectors. So what is this term? This is nothing but the sample mean. Right, this is the sample mean. So you can think of these x1, x2, xn as observations of some random variable x. So if this x is distributed according to some distribution, p of x given some c. Okay, that is indirectly we are writing it in terms of p of x given mu, where the mu is unknown, and the mu that maximizes is the mu hat. So, so these x's are actually independently drawn samples from this unknown p of x given c. So this forms a sample. So like we are talking like in statistics, no? When there is a population which is represented by this random variable x, and we are drawing a sample of n observations from this population. So this is your set of samples, n samples, and this you get the sample, and its mean is the sample mean. Okay, so traditionally sample mean is usually written as x bar. Or I'm not sure if it is, sometimes it may be written as x bar. I'm not sure. I may be using both notations. So it's just written as x bar usually, the sample mean. Okay, so this is a what do you say? This is a intuitive result, because if you are given a set of data and you want to estimate the mu, okay, then we just estimate it by approximating mu as the sample mean. So what is the difference between mu and mu hat? This mu hat is same as mu ml. Okay. Mu hat ml, whatever I wrote. Yeah, what is the difference between mu and mu hat? What is the difference between mu and mu hat? Vikas Singh, are you there? Vikas Singh John.
Yes, sir.
Okay, what is it? Can you tell me what is the difference between mu and mu hat? What is mu?
Actually, I was about to look at the lecture afterwards because I'm not paying attention right now.
But do you know what is mu?
Yes, sir. It's a mean.
No, mean is a very vague, very ambiguous way of saying something. There is. Can you tell precisely what is mu?
No, sir.
Somebody who can say what is mu? What is mu? Akansha Gautam, do you know what is mu? Akansha Gautam is not there. Nalin Agarwal, can you say what is mu?
Sir, it's
What
a
is mu?
parameter used here.
Huh?
So mu hat is optimal mu.
Mu hat is not optimal mu. So, okay, this mu is different from the whatever mu I wrote here. Don't worry, don't consider this mu. This mu that we are saying in terms of the parameter that you don't do. I'm telling in general what is mu. Given this population X, what is the connection between X and mu? What is the connection between X and mu? Ashish Rana.
Sir, mu hat is the sir, uh, like what is the maximum likelihood? Like,
I'm not asking about mu hat. Mu hat is clear to us. It is a sample mean. That is fine. I'm
hmm,
asking about mu. What is mu in terms of this X?
uh, sorry, sir, not able to tell.
Anybody else? Some of the math students? Any PG student? Can you say what is mu? J and Sharma, CSP.
Yes, sir.
What is mu?
So mu is something around which all the samples have the value. It is an
Don't explain. You give me a precise answer for what is mu. Mu is this mu which I'm talking about is expected value of X. Yeah, mute yourself, Jay. Mu is the expected value of X. X is the population. X is the underlying random variable from which these samples are drawn. And mu is the true mean of the population, which is nothing but the expected value of X. What we are finding out here is the sample mean. So mu and mu hat are different. Okay, when will mu and mu hat be the same? It will become same only if you have a large number of samples, an infinite number of samples. If this n tends to infinity, then your mu hat will become closer and closer to the true mean. Okay, and what is this mu hat? Mu hat is a sample mean. Is that a random variable? Is mu hat the ML estimate of the mean? Is that a random variable or is it not? It's not a random variable. What can you say? Prachi, are you there?
Yes, sir.
What can you say about the sample mean? Is that a random variable?
So maybe if we take a different sample, then it can change.
Yes, it is a random variable. Yes, the sample mean, what we said here, X, is also a random variable. This is your ML, mu ML, which was mu hat ML. So this itself is a random variable. So you should be able to find out what is the expected value of X bar. I mean, my notation is not very concise. I mean, it's not very consistent. Sometimes I'm writing X bar and sometimes I'm writing capital X bar. But essentially, this is the sample mean. So the X bar here is the sample mean. This is essentially same. Okay. Yeah. So expected value of the sample mean. Okay, and it can be shown that the expected value of sample mean is actually equal to mu, which is actually equal to EFX. It can be shown that the expected value of the sample mean is equal to the true mean. Okay, so this estimate, the estimate of mu is a correct estimate. It can be shown that, so I think in the tomorrow's lecture we will see that when you estimate the maximum likelihood estimate of variance, then this condition does not hold. So that means the expected value of the sample variance, because the ML estimate, the maximum likelihood estimate of variance, is going to give you not sample variance, it is going to give you average of the variation from the mean that we will see it tomorrow. And that average is not equal to the sample variance. So in summary, the maximum likelihood estimate of mean is correct, but the maximum likelihood estimate of variance is underestimates the variance. So it's a biased estimate of variance, of the true variance. Okay, anyway, hopefully don't know about the landslide, but this is all there in Luda Hart's book, so please look at it. And I'll stop here and we can meet on Thursday. Fine. Okay, if you have any questions, just let me know. I will upload these notes. But please do try and work this out. Okay. Yeah, you can leave.